Keerthi thinks that substitution reaction occurs in saturated hydrocarbons. On the contrary, Krishi thinks it occurs in unsaturated hydrocarbons. Justify with valid reasoning whose thinking is correct. Let's first see the key characteristics of saturated and unsaturated hydrocarbons. Saturated hydrocarbons have single bonds, where each bond is attached to an atom. They are highly stable, so it's not possible to add another atom, and they react with halogens via halogenation, which substitutes a hydrogen atom with a halogen atom. On the other hand, unsaturated hydrocarbons have double or triple bonds, where two or three bonds are attached to the same atom. They have unstable pi bonds that can be broken easily. So they undergo addition reactions where hydrogen is added to convert an unsaturated hydrocarbon to a saturated hydrocarbon. Thus, Keerthi's thinking is correct as substitution reaction occurs in saturated hydrocarbons. Hydrogen atoms are replaced with heteroatoms in saturated hydrocarbons. Whereas in unsaturated hydrocarbons, an addition reaction occurs. Simple molecules are added across double or triple bonds. Second part of the question is methane and propane and their isomers are used as fuels. Comment. Also draw the electron dot structure of the immediate lower homologue of propane. Give any two characteristics of homologues of a given homologous series. Now, both methane and propane produce a substantial amount of heat when burned, making them valuable for generating energy. Methane is the primary component of natural gas, while propane is readily extracted from petroleum, making them widely accessible. When completely combusted, they primarily produce carbon dioxide and water, considered relatively cleaner compared to some other fuels. Even though isomers have different structural arrangements, they generally share similar combustion properties, making them useful as fuels. Thus, we can conclude that methane and propane, along with their isomers, are used as fuels because they readily undergo combustion reactions, releasing a significant amount of energy when burned, making them efficient fuel sources with readily available hydrogen atoms to react with oxygen. Next is draw the electron dot structure of the immediate lower homologue of propane. Now, the lower homologue of propane is ethane. Its electron dot structure is this, where two carbon atoms are singly bonded to each other, with each carbon atom further bonded to three hydrogen atoms, resulting in a structure where each carbon is surrounded by eight valence electrons, that is a complete octet, and each hydrogen has two electrons, a duet, fulfilling the octet rule. And finally, two key characteristics of homologues within homologous series are, let's first get to know what a homologous series is. So, it is a series of carbon compounds that have different number of carbon atoms but contain the same functional group. For example, methane, ethane, propane, butane, etc. They are all parts of the alkane homologous series. Two key characteristics of homologues within a homologous series are all members of a homologous series have the same functional group, which is a specific group of atoms responsible for the characteristic chemical reactions of that series. When moving from one homologue to the next in a series, the only difference is the addition of one more CH2 group to the carbon chain, leading to a predictable increase in molecular weight and often a gradual change in physical properties like boiling point. Interesting, right? Now, the last part of the question is a mixture of oxygen and ethyne is burnt for welding. Can you predict why a mixture of ethyne and air is not used? Well, a mixture of ethyne, that is acetylene, and air is not used for welding because burning ethyne in air produce a sooty flame due, due to incomplete combustion, which doesn't reach the high temperature needed to melt metals for welding. Instead, pure oxygen is used to create a clean, extremely hot flame with ethyne for welding purposes.